Hi, everyone. Welcome to Foresight's Molecular Machines Group. I'm really delighted today to have Dr. Chengde Mao here with us today in the seminar to present on the simple side of DNA self-assembly. I'm going to share more info about you here in the chat with people, and I will also share a new in-person event that we have coming up in our Molecular Machines Group for those of you that want to join that in October. We have Eric Drexler coming to San Francisco, and then a really wonderful molecular nanotechnology workshop as well. So I will be sharing a little bit about that here in the chat. But for now, we are very delighted to have you here. Thank you so much for joining us. And without further ado, the stage is yours. Please take it away.
Yeah. Thank you guys very much. Have this opportunity to share with you about my research on DNA self-assembly. DNA nanotechnology or DNA self-assembly, it's really started with Richard Feynman. So he proposed this idea to use branched DNA. Okay, anyway, I tried. Okay, I see. Here is another point. So use this branched DNA structure, and at the end, he introduce a thickened at least one strand, like here is longer than the other strand. This single-stranded end, if they find another single-stranded end, they could complement to each other and hold cells together. And then, this branch, if the top thickened and the bottom thickened are complementary to each other, then the molecule can associate along this vertical directions. At the same time, they could associate in these horizontal directions, like here. In that case, they will form a two-dimensional arrays. So the overall idea is very simple and straightforward. However, I would before I go on, I would say this exact design never realized. But from here, we get many other things. Over the years, many very beautiful, very complicated structure are built based on these simple ideas. For example, the Richard Feynman himself built this cube. This is structure for a long time. It's a symbol of DNA nanotechnologies. And this Lulu Chia at Caltech self-assembled DNA structure into this Mona Lisa structure, and Paul Rossmann made this smiley face structure. That is a real revolution idea for this field. So introduce GAMI approach that these days is pretty much equivalent to DNA nanotechnologies. When you talk DNA nanotechnology, people are immediately associated with origamis. And along this same idea, Hendrik built this very gigantic structure. How Yan made this very beautiful, vast structure. And he's saying his law is with this flower vase law, trying to build flowers. And this Peng Yin at Harvard made this teddy bear structure, is a micron scale structure. And it's not only beautiful, it's also this structure can be functional. For example, Bao Chuan Ding at Beijing, he built this drug delivery vehicle to deliver drugs. Like here is purple molecule, these drugs. So when they delivery, they enclosed in a DNA nanotube. But when they go to this target site, they open up, so the drug can activate the biological process to kill cancer cells. More recently, Tim Liddell in Munich, he developed a strategy to assemble DNA origami structure like this tetrapod structure into a diamond lattice. And this diamond lattice, after coating with silica, they can serve as photonic crystals. This work is just recently published in Science. It's great with DNA self-assembly based on this very simple idea proposed by Richard Feynman in the early 80s. Now people take those ideas that they can develop into a very complicated structure, very beautiful structure, and they could be very functional to generate new materials. To myself, I Instead of pursuing this very complicated structure, I go to the other side, go to simple. So my overall philosophy is this way. At the end, for the DNA nanotechnology, if we find the real useful things, when we put it into practical applications, we must make it simple. When I say simple, means two things. First of all, the construction materials need to be simple. Like you build a building, you don't want to have hundreds of different building materials. If we can narrow down to just a few building blocks, that is much easier to handle. And another side, I say simple, is the process should be simple. That means they should be robust, reproducible, and if people to learn this assembly, they should be assemble those guys just after a very brief training. We say one afternoon or one day training, they can assemble instruction. That is what I say the simple process. So two things, simple building block, simple process. This just give you one example to talk about the simplicity. Supposedly, we want to build a square like on the right side. If it's you can have two different approach. They are complementary to each other. One I call it this asymmetric approach. You make four different building blocks: red, blue, purple, and green, and you make this thick end. This end interact with this one. This end interact with this one, and so on. You put this four building block into the solution, and they could find each other, and then they assemble into a square. That's correct. Another approach, I call it this symmetric approach. You make one building block, and then you make this angle precisely to be 90-degree angle. And this second can interact with this one in the solution. Four of these guys, they can assemble together for the square. Now, the trick here for this symmetric approach, you need to precisely control this 90-degree angle. These two approach, they have advantages, disadvantages. First, if you look at the asymmetrical approach, this is a general applicable strategy. You can use this strategy to assemble pretty much any complicated structure. In these days, this particular origami or single-stranded tile approach, you pretty much we can confidently say you can assemble any complicated structure at the nanoscales. And the design is very easy. It's very robust, very easy to design this one. The only downside with this asymmetric approach, because everywhere is different, you need to use multiple component blocks, many DNA strands. For example, like the DNA origami, like early on we showed there's a smiley face. You need 300 DNA strands plus one very long DNA strand, a lot of DNA synthesis. On the opposite direction, use this symmetric approach. This one, because you take symmetry, like here, the square, you have a 4-fold rotation symmetry, so you can design this guy with just one building block, will make it a 90-degree angle. This intrinsically, you only can assemble this moderately complicated structure. Quite often involved the high symmetry involved. And the design is a very difficult design, we should keep in mind. It's a very difficult design. You really need to understand the DNA structures. For example, here, the 90-degree angle design, that is not an easy job. You really need to study this design and optimize the design. That's a lot of work. The payoff is at the end, if you find this right design, so then the component is very simple. It's just one building block with minimal DNA strands. What I say minimal, it's normally is only involved like 3 to 5 different strands. So now you can say the difference between these two approaches. The top one, its design is simple, but then you need to involve hundreds different DNA strands. The lower one, the design is hard, but at the end, you only need to involve 3 or 5 different DNA strands. So this depends on what you want to do. At the early stage of the research, you want to quickly build some structure for as a prototype. That's absolutely want to go to the top choice. But at the end, if you want to build something to go to this market, to go to the customer, you absolutely want to strive to introduce this symmetric approach to make things easier. Over the years, in my group, we really pursue on the symmetric approach, make things simple. So, for example, if you want to make a DNA 2D crystals, you will have this red strand, this green strand, and you have the red strand, the green strand, and one with this black strand. For example, this you have this one and this molecule. This strand is a repetitive sequence. You repeat 4 times. You combine together, there will form a 4 branch structure. Then, if this outside have stick end, then it will assemble into this tetragonal lattice. But now, if you say, I don't use this strand, instead I use this one. This one is still a secondary molecule, but they repeat only 3 times. Then you get this 3 branch structure. Then with the stick end, you get the honeycomb structure. So it depends on which black strand you use. Then you get different DNA blocks. These different DNA blocks, they assemble into different DNA 2D arrays. These DNA 2D arrays certainly have their own good thing. So they have a real DNA symmetry. So if you talk about use this one as template to templating protein crystallization in this 2D sense for determining the crystal structure, this will be perfect substrate to use. This is not only limited on 2Ds. You can also apply the similar philosophy into a DNA nano cage. The simplest DNA nano cage is a DNA polyhedron. So you take those 3 different DNA strands, you combine them together, they form a 3 branch structure. Now the middle here, the single, this red segment, that is a single DNA strand region. That gives you this molecule flexibility. It depends on what single strand region you use, then this overall building block will have different flexibility. If you tune it, this guy can bend, just a fly of this guy can form a tetrahedron. So you can imagine here each corner is 1 building block. 2 this building block contact together, they forms 1 edge. So that is the overall idea you go it. Over the years, we can use this idea to build one array of DNA nano cages. So all these DNA nano cages, if you look at the overall size, is somewhere between 10 to 100 nanometer. Here I want to remind you, for this virus, the natural virus, for those systemic virus, for example, like a COVID-19, those group of virus, the size is somewhere between 20 and 200 nanometers. So that is pretty much comparable with those nanostructures. That intrigues us to explore those nano cages. There's biological applications, for example, like vaccines. Here, those are DNA nano cages. When you produce, this is each structure here I shows is only made from 3 to 5 different DNA strands. So you can contrast this structure with a DNA origami approach. DNA origami approach that they can easily make the structure, but that requires several hundred DNA strands. So if you want, again, if you want to make this structure in a very quick time scale, to explore different structures, DNA origami is the choice. That's no question about. But if you want to go to this, talk about real applications, in this, at the end, you want to put it into market, I would argue those symmetric approach might have their own advantages. We also explore this engineering DNA into 3D crystals For example, like earlier I mentioned this, Tindido use a DNA crystal to engineer this photonic crystals for this photonics applications. We explored this one is quite early from 2003 or something like that. So the first structure we engineered is we call this one is a DNA tensilic triangle. On this left here, that is it's a structure model. It's really example this building block. This photo is I took this photo at Arizona once I visited my friend Hao Yan at ASU. So in this structure, you can imagine each rod here is DNA duplex. And 3D duplex come together, joined at the here like this way, they join together, both are triangle. This one we call the triangle, but obviously it's not a real triangle, but because this is not flat. But now if you think about it, this each rod here is a duplex. If the end we add stick end, like here this is colored in red, if they can associate this triangle associated with this each DNA along each DNA duplex, then at the end they can associate into this DNA crystals. This is our design. We make this DNA building block. Again, this DNA triangle made 3 different DNA strands, the green, the blue, and the green. You put it together, then you concentrate in the solution, then this guy will associate together into this DNA crystals. This is the crystal you got. And from this crystal, you can pick to the X-ray to the diffraction, you get a diffraction pattern. From the diffraction pattern, then you can calculate back to confirm the DNA really assembled in the way we designed. So this is the structure we finally got. Here, I want to make it very clear. As one says, looks like what we are doing is exactly the same way that the structural biologists are doing, right? You start with one molecule, you crystallize, then you take the single crystal, go to the X-ray, deflect, and then from the diffraction pattern, you get the structure. However, there is a major difference. For the structural biologists, what they are interested in is to go through this process to determine there's an original building block, what the structure it is. They are interested in to determine the individual molecule, the structure it is. Before they go to the last step, they really have no idea what is the molecule, the structure it is. We are exactly the opposite. So what we are working on is to have this molecule to get the knowledge from the structural biologists. So then we engineer the molecule to assemble into a crystal of our interest. So what that said is, that means if our understanding is correct, our design principle is correct, before we do any experiment, we should be precisely predict this crystal, what the molecule arrange themselves. And each atom go to exactly what position. We should be able to precisely predict that. Of course, I should admit this one. In current state, most of our prediction is wrong. Our design doesn't work. That is the phase and for now. But hopefully, as our experience get more, our knowledge are better, we understand the principle better, we have better and better prediction power. That is the hope. Well, for the DNA crystal engineering DNA crystal, when we assemble the crystal, we want these interactions between the building blocks be as weak as possible, because only weak interaction allows the assembly process to be reversible. But now, after we assemble the crystal, when we talk about the applications, when we want to use the crystal to do some things, we want the crystal be robust. This is problem, the intrinsic problem. Over the years, we found a different approach to solve this problem. But at the end, we found actually there is a very simple approach to solve the problem is by ligate the DNA crystal. So this one. So when we assemble this crystal, each between the building blocks, the interaction is by hydrogen bonding. It's weak. But so what we found is one way to overcome this problem is by ligation. So there is a in the nature, in the cell, they have a DNA ligase. What they do is to convert this covalent join into a covalent bonding. By that way, the DNA get a covalent bond, then the crystal becomes a very stable structure. In a sense, you can say this one is a supramolecular assembly for this beginning, but after assembly, this is a covalently joined crystal. Yeah, this one becomes very tough. So that is our design, what we have. So before we assemble here, we made a further analysis. We look at in the solution, we ligate them. So you can see this one, the ligation is very efficient. For example, this one, this lane is completely without ligation. We try to ligate this molecule. This one completely disappeared. Instead, it's a series of upper band sub-ligated generated. So you can say this one, the ligation is very efficient. So this here is different lane. It's just we try to ligate different molecule. But after ligation, the crystallinity, the structures remains. That is the most important thing. So if you look at the TM image, you say this is crystallinity still be there. That's great. Ligation, then the crystal becomes extremely robust. So if you the high temperature, for example, 65 degrees for 16 hours, the crystal still remains intact. Just to give you a contrast, if without ligation, normally only 2 or 3 degrees increase by temperature, the crystal will completely dissolve. The crystal also can survive for dehydration. So the crystal, if you dehydrate and it is dry, the crystal collapses. But as long as you add water in, the crystal pop back. So they can memorize their original structures, that is nice. And if you get rid of the salt, the crystal still be fine. If you apply a mechanical force, and so here we use a tweezer to push onto the crystal and scratch along the surface several times, but the crystal still remains. That's nice. And also they can survive with the chemical changes. So when you stain the crystal with different dyes, then if without ligation, the crystal will just crack. But after ligation, the crystal can stay with all these dye changes, they still be perfectly fine. And more interestingly, this ligation also allows us to make some exotic crystal architectures. For example, here you start with one crystal, you like it, but you like it only very short time. So the ligase can go on to the very outside of the surface of the crystal, but cannot ligate the inside. Then after a short time ligation, you can dissolve the inside of the crystal. Then you only get a crystal shell, but the inside is empty. Then you can use this shell as a seed to glow crystal outside, go further, and then you repeat this process again. Then you get them 2 layers of these crystal shells, and then you can go on, get the multiple layers of crystal shells. That is pretty much Russian door structures at the end. And if you look at the crystal, if you only like it in 2 directions, leave the third direction unligated. So then what will happen is you take the crystal, ligate it only 2 dimensions, but the third direction, if you add EDTA, remove this mechanism, then the in this third dimension, in this height direction of the crystal, the thicker end associating will dissociate. Then the crystal will expand. So you are expanding, you say this is a process that first generate wrinkle and they expand, but at the end, you get a expanded crystal. But you add the mechanism, then the crystal contract again. And then you can repeat this process to expand the contract over again. So this becomes an expandable crystal. And this expandable crystal here is only shows with this metal, but later on you can tune this condition to let it respond to short temperature, pH, ETA, or redox potential. So it becomes a sensing mechanism. And with this sensing mechanism, you can use this expandable crystal to capture molecule and release molecules. You can think about this for drug delivery or something. That is the work, nice tool, right? So you start with the crystal. You at the expanded condition, you let this other gas molecule, in this case is a green fluorescence protein, to diffuse into the crystal, because like here, now if you squeeze the crystal, let the crystal contract, then they squeeze out this gas molecule to release. So that is, you can imagine this will be a storage or delivery mechanism, this one. We are really pushing on to this crystal engineering, try to get high resolution crystals. That means you can have better production power of the crystal assemblies. This probably is the, so far the best engineered crystals. In here, we use one single strand DNA. So it starts from here, this blue domain, and then go to red domain here. This single strand DNA, they can self-dimerize into a structure like this. And this guy, they can further associate. If we associate them along this red domain, then this will be like this way. You have one building block, second one, third one, and the fourth one. Each one, when they go along from lower to higher, they will rotate 90 degree. So at the end, they will associate into a crystal like this one, the P4322 phase group. Yeah, they can assemble nicely. And if you put one domain, for example, like here's the red domain with small molecule binding domain, for example, like Hawk's dye, here's the binding domain, then they can co-crystallize into this one. Only the bright light, they show the crystal. If under the UV light, they shows this fluorescence because this molecule is a fluorescent molecules. And from here, you can resolve this structure, how the crystal bound. Other one, this blue molecule, this the Hawk's dye, and they show this molecule how they bind to here. Let me go back to one more step. This is one is really pushing on to this idea to use DNA as a host molecule. You engineer the DNA into crystal to study how small molecule and DNA the interactions. That's this type of information will be very critical for us to design small molecule interact with DNA molecules. That's for the pharmaceutical industry. That is extremely important for to develop small molecules to target onto DNA specific DNA sequence to regulate gene expression or genome editing or this kind of things. I mentioned this. We say the assembly, the building block should be simple. And another thing is the process should be simple. Now, currently, the process, we will always start with a single DNA strand and then let's assemble and so on. But now, if we think about biology, for the biologists, what they got for the DNA from the nanometer-scale reaction, they always get a duplex. They cannot get a single-strand DNA. Actually, for you prepare long single-strand DNA, that's a lot of trivial job. Right? You can do it, but you never get large quantities. So that will be highly desirable if you can develop a strategy to use DNA duplex as starting materials without isolate just a single-stranded DNA. That would be ideal. So that is one effort along that directions. Supposedly, you after get this DNA duplex, either you isolate from the cell or you from PCR reaction, whatever, you get a duplex DNA. If this DNA, duplex DNA designed in such a way, they could assemble separately, go to design the DNA structure. That would be cool. So this is exactly what will happen. Okay, we designed this guy, and this was two strand. You increase temperature, so this DNA duplex dissociate separately into two single strand DNA, and then you quickly quench to very low temperature. Then those guys they will self-fold into this structure or this structure. So in here, most of the DNA bases, they fold into DNA duplex. Only leave very few DNA single-strand region exposed. In such a way, then they don't hybridize together, forms that go back to the duplex. But here, then you add magnesium, then there's a long range, there's a single-stranded region, they can further interact with each other, forms the desired structure. For example, here, this forms a triangle. So this here indicates this exactly how this single-strand region they interact with each other. So this is the design process, right? If you want to design a triangle, then you decide where is the and the loop inertia, here the loop inertia. So you fold this guy into this structure and they introduce a loop inertia here. So this is it's just an different image to show the triangle assembly. This one, you can see here, if you go after you come to this stage, if you go to a slow ideal to letting temperature slowly cooling down, these two strands, they can find each other, go back to duplex. But if you quench, go very quickly lower temperature, they cannot find each other. Instead, there's an interim strand that fold into the target structure. So this is the exact how. So if we lower the temperature slowly, you form duplex. But if you quench very quickly, they forms dominantly forms this duplex or forms this triangle. You still have a little bit duplex remain. So in this in this F image, you can see here is the remaining minor duplex, but majority they form this triangle. This idea you can form some certain more complicated structure. For example, like here, there's a figure 8, or here you have a four square structure, like the image shows here. This is a Chinese lock structure. You can get here. This is the last piece of work I want to share. This will take this idea not only can produce DNA in this test tube, will also be able to produce engineered nucleic acid structure inside of cells. Well, of course, inside of cell, they have quite some limitations. Inside of cell, you cannot produce single-stranded DNA. I could take it back. It's not easy to produce single-stranded DNA. But on the other side, you have a lot of single-stranded RNA molecules. So we decided inside of cell, instead of use DNA, we use RNA as the build molecules to produce nanostructures. Another thing is inside of the cell, you cannot do this thermal treatment. You cannot heat up to with 90 degrees and then cool down slowly or quickly. For the cell, if you do this, all the cell dies, right? So you should develop the strategy only isothermally assemble at this 37 degree or room temperatures. So here is the overall ideas. We design a piece of DNA molecule. This piece of DNA molecule is the code with one RNA molecule inside of the cell, put in the plasmid. as long as this transcription goes on to synthesize, the RNA molecule will fold while they transcribe to these targeting structures. When the transcription finishes, they will release this target RNA molecules, the nanostructures. That is our design. Instead of here, I want to go forward. So this is the idea. So supposedly, we want to make a DNA square. You design this, or the RNA square. You design this RNA molecule in such a way they can first fold into a secondary structure with mostly a duplex, but with a few single-strand region, these loops. And then this single-strand region in the potential mechanism, they can further interact with each other to form a square like here. So this four loop, they give a longitudinal angle, and here this loop will interact with each other by Christian loop interaction like here, then they will form a square. That is the idea. So this is what we designed for the square. You can see here for the square. Now, if we purposely design this RNA molecule in such a way, this loop, they're not interact with each other. That is the control molecule. So you will see here is always be open here instead of closed loop square structures. So you can also make this guy form the figure 8 structure. So you form this figure 8 structure here. Then they form the flower structure, or form the four square structure, form the tetrahedron structure that brought by RNA. So here I want to point out is this one is a co-transcriptional process. This is outside of cell. We first want to prove this folding strategy, co-transcription folding can work at an isothermal process. So without the quick treatment, they can RNA, while they transcribe, they can automatically fold into the right structure. But at the end, we prove this can also be done inside of cells. So this is how we construct the plasmid into the cell, then introduce a fold. So now you can see here, it's there. Before I go on to this explanation, I want to say, I want to explain what we did. So we close the cell, introduce the RNA expression, and then let the cell centrifuge get rid of these large pieces, debris like membrane or this sense, and then take this aqueous solution directly deposit on cell surface to image it without any other fragmentation or purification whatsoever. So to really minimize any post process, to make sure what the structure will observe is really exists inside of cells. So that means at the same time, beyond this RNA structure, they also have a lot of this cellular molecules like proteins, ribosomes, whatever, right? So here in the first on the right or on the left, we get a lot of the random structure that is from the cells, the proteins, whatever. And in the middle, this is with plasmid, but without the RNA expression. Again, you get all these random things. But the last one, on the right, this is with plasmid and induced RNA expression. So make sure the gene gets transcribed. Then you say here this figure 8 structure. That's what there is no mistake, right? Inside of a cell, there is never have this type of structure. So it's very clear that is the structure we engineered. Hopefully, by now I shared with you of our research on this one to make how to make the DNA self-assembly simple, make the structure building block simple, and make the assembly process simple. Then we can use this approach. We can assemble a range of moderately complicated structures. But of course, the question always remains how far we can go, how complicated the structure can go, or is there any room can make the structure assembly even more simple. At the end, I want to acknowledge they supported over the years mostly by NSF. We are very focused on small group here. And also, I would like to thank all my collaborators. And thank you all for your listen. And I will be very happy if you have any questions.
Fantastic. Thank you so much. I learned a lot. Thank you so very much. I will give it up to questions first from the audience. We already have the first raised hand. Are you okay to take it? Is now a good time? Okay,
Yeah,
cool.
yes.
Then Ted, take it away, please. Unmute yourself
Thanks.
and ask your question.
Yeah, thanks so much for presenting to this group. I was really glad to see you. So my question has to do with you described a variety of ways of making intricate structures with DNA, and they possibly could be functionalized, to give some logic, as you mentioned early on, for like drug release. One of my things I was wondering is whether this could also lead to multi-step machines that can exert forces in response to signals such as cyclic changes in pressure or chemicals or temperature, somewhat like you illustrated with the DNA sponge that expands to absorb molecules and then compressing to expel them. Do you see a way you could use these or design and then assemble structures that could do mechanical operations cyclically?
Yes, actually, I think that is our group also did quite some work on that side. And in this field, we call this one as nanomotor, nanomachine, or whatever. So they make some movement in the controllable way. Yes, we can do that one. So there are multiple ways to make it. So the currently most powerful way is by we call it strand displacement. This way introduced by Berger and Timmerfield. That is a very powerful way to do it. But other way we also can use it is by introduce a chemical change, or by response to light or electric signal. Yes, I think that is really quite easy to implement.
There's a lot of very flexible structures and capabilities there. Yeah, thank you.
Thanks.
Wonderful. Micah, you're up next.
I've got a simple question. When you mix together all the parts for the 3D crystal that you did, do you end up with one very large crystal in the solution, or do you end up with a bunch of crystals of a wide variety of sizes, and then you just pick out one to image?
Depends on what crystal you talk about. The crystal, for the single crystal, we'll get currently in the group, we'll get like 7 millimeters long for the large one. But that is outline. In most of the cases, we get the crystal get like 100 to 300 micrometers in that size.
Do you know what the limiting factor is? Like, why is it that they don't grow indefinitely? What prevents you from making 1 meter size crystals? Is it just you don't have big enough vat, or is it some structural thing that falls apart?
I would say 2 things. Intrinsically, when the crystal glows, if you can limit the nuclei numbers, then they only have a few nuclei, then they can glow larger. So that is one thing. Second thing is you reduce the defects during the assembly. So what happens quite often is when you assemble, you will introduce defects along the way. When the defects glow too much, then the basically crystallization process stops. That is the second thing. The third thing, I would say, don't underestimate the cost. We just simply don't have that much money to explore to the millimeter size. I would say that one. We certainly do have quite some idea to get the crystal large. Then currently, I think we don't have that resource to do that. So then the overall idea, what I say is one idea to say glow is a large crystal. I'm thinking is like the silicon wafers, the glow silicon wafers, right? You think about silicon wafer, how they glow, make this single crystal silicon wafer. They glow very large crystals, and then afterwards, the one which have a real process, right? The local heating to dissolve and then put it in the heating room and move to after they move. Basically, that's a leading process to get it sorted. For the DNA crystal, I would imagine we can do something similar, either in thermally or chemically ideal to get it to glow. Yeah. But again, at this moment, we haven't really pursued that, but mostly because of the resource limit.
Excellent. Thank you.
Wonderful. Okay, I have a few questions that most people here always want the answer to. They're a little bit more standardized, but one of them usually is if you could extrapolate outward, like the possible application space, and let's say 5 years or something, if you guys are continuing to make progress as you do right now, like where could we see possible applications, in which sectors, in which spaces do you think, where could we see an impact on this in real world applications?
Yeah. So our group, that like this slide shows, it's quite a small group. So we are really focused on those develop this basic assembly strategies to instead of to directly face onto the application, we are more on the basic side. That is the one that I'm thinking for the, like a small group, like instead of to do everything by ourselves, the better to focus on just one subset of in this field to then we can go deeper, generate impact that one. But in terms of application, we do have quite something in our mind. So one first thing is in this biomedical side. For example, like the last several years, we experienced this COVID, this pandemic. That's a really big impact to the society. So one thing we are thinking for this vaccine development. Of course, now this mRNA vaccine, that is it's really attracting people's attention. But they do have a lot of other alternatives to develop vaccines. One particular one, what we think is to take those DNA nanocages to decorate those molecules, like we say, this spike protein from COVID virus, to decorate onto those building multivalent display platform with a universal platform. It's uniform size, multivalent. You control this geometric distribution, and those I would imagine actually will be a wonderful to create immune response. This one, and with this one, you can imagine, for example, this molecule. At the end, this declaration is just like a real virus, right? This you have all these proteins, antigens outside. Inside, you have nucleic acid. With the nucleic acid, suddenly you can introduce all this to stimulate the immune response. So that is one direction. And certainly this one also, you have many other things like drug delivery. I would imagine it's a very good form here. So that is one side. Another side is on this physical devices. Like, for example, like this one, this Chengde Mao built this photonic crystals here. This crystal, what they use is the DNA origami, and this one, again, just like what I said earlier, we try to demonstrate this idea. The DNA origami, that is a wonderful choice. You actually want to go that one, right? And so allow you quickly to explore the different structure, the structure parameter, how they influence the property of the photonic crystal. However, you think about it, at the end, if you want to use real build this photonic crystal for applications, you don't want to use several hundreds of DNA strands to synthesize several hundred DNA strands. This is so complicated structure to make this one. In that case, you certainly want to develop a strategy, implement the symmetry to make those guys made from just several DNA strands. That way, the cost will greatly drop, and the assembly of baskets will dramatically increase. So that is something we think our research could contribute. Yeah.
Cool. And we just have a follow-up question here from the chat. If you could compare for us here the advantages of DNA versus RNA nanostructures.
Yeah, that is a great questions. for this, if we think about it for this outside of cell applications, I think DNA will be probably you are first to think about DNA because DNA is more robust, is chemically more stable. RNA on the other side is much less stable, is much more fragile, and chemically because the RNAs and that everywhere they were integrated. But however, in some cases, we have no choice. You have to go with RNA. Inside of a cell, for example, you want to interference with the cellular process. Inside of cell, they can generate a single-strand RNA easily, abundantly. So in those cases, you want to take advantage of RNA. In addition to this, RNA also have more chemical functionalities. The binding activity, the catalysis, all sorts of things. So in those cases, RNA certainly will add up.
All right, awesome. I want to be mindful of your time here, so we close on time. So sorry, Ted, but I just want to make sure that we ask the last question often here. If people are excited about your work, how can they help you contribute? What's currently an outstanding challenge? And either are you, for example, hiring new folks? Are you looking for specific collaborations? Is there anything how people that are excited about your work can help you?
Oh, yes, that's absolutely. Anything I would think. So just like what I mentioned earlier, our group mostly focus on this fundamental development of these strategies. Like this applications you mentioned earlier, we talked about this one. Those part I would more leave on to collaborations. If any people have any idea that this one could be used for, even though the structure is not available now, if they let us know, we certainly will be very happy to develop the structure and to explore all these applications. Yeah.
Fantastic. With that, I really just want to thank you so much for taking the time to come and present your work. It's really fantastic. I love that you're so application and functionality oriented. We need much more of that, I think, to connect the practice with, I think, the really interesting science that's behind it. So thank you so much for coming on. It was really fantastic. I learned so much. And I wish you all the best of luck and much success with your work. And we hope that it wasn't the last time that we saw you in a seminar here. Thank you very much.